Hey, got that IT-709 AI exam breathing down your neck? Well, you're in exactly the right place. Seriously, think of me as your personal tutor for this last-minute cram session. We're going to go through every single key formula from week 6 all the way to 11. My goal is to make sure you don't just memorize this stuff, but you actually understand it, all right? Let's get this done.
So here's our roadmap. First, we're going to tackle how to draw lives to classify data with support vector machines. Then we'll get into predicting actual numbers with regression. After that, we'll play detective and find hidden groups using k-means, then build a mini brain with neural networks. And finally, we'll cover how to get images ready for an AI, and crucially, how to grade our models to see if they're any good. By the time we're done, you'll see how this all clicks together.
All right, first up to bat, support vector machines, or SVMs. So just imagine you've got a bunch of data points on a chart. Maybe some are cats, some are dogs. The entire goal of an SVM is to draw a line that separates the cats from the dogs, but not just any line. We want the one that creates the biggest, widest, safest possible gap between them. It's all about separating with maximum confidence.
Now, this little formula, W times X plus B equals 0, this is the absolute heart of the SVM. This hyperplane is basically your decision boundary, your wall. Think of W as the weights that control the angle of the wall. X is your new data point, your new cat or dog, and B is a bias that just kind of shifts the wall left or right. So let's do a quick example. Imagine your weight vector W is 2, 1, your new data point X is 3, -4, and your bias B is -1. You just plug it in. 2 times 3 plus 1 times -4 minus 1. That's 6 minus 4 minus 1, which gives you a positive 1. Because the result is positive, the model shouts, "That's class 1." If it had been negative, it would have been the other class. See? That's the decision rule right there.
Okay, so how do we know if we've built a good wall? We measure the margin. Think of the margin as a two-lane street between your two groups of data. The wider the street, the better. The formula for that width is 2 divided by the magnitude of W. So if our W vector was 3, 4, its magnitude is just the square root of 3 squared plus 4 squared, which is the square root of 25. So 5. The margin is 2 divided by 5, or 0.4. The key is that a smaller W vector gives you a wider street, and that's what we want. But what if you can't draw a straight line to separate your data? That's where you use a clever trick called the RBF kernel. It basically bumps your data into a higher dimension where a straight line does work. It's kind of like a cheat code.
So listen up, this is a huge exam tip. Write this down. The core concept of SVM isn't just about separating data. It's about finding that one single optimal line that makes the margin as wide as humanly possible. If you get a question that asks you to pick between two SVM models, the answer is always the one with the bigger margin. Why? Because it's more robust and less likely to mess up on new data it hasn't seen before.
All right, time to switch gears. We've been sorting data into boxes, right? Cats, dogs. But what if you don't want to sort? What if you want to predict an actual number, like the price of a car or the temperature an hour from now? That's when we bring in regression. We're shifting from asking which category to asking how much.
So, for any prediction model, we have to know how wrong it is. We have to measure the error. Let's use a house price example. Say the actual price of a house is $300,000, but your model predicted $280,000. The error is 20K. For another house, the actual is $500K, and you predicted $510K. The error is -10K. Now, for MAE, mean absolute error, you just take the average of the absolute values. So the absolute of 20K plus the absolute of -10K divided by 2, that's an average error of 15K. But for MSE, mean squared error, you square the errors first. So you get 20K squared plus -10K squared, then average that. Notice how that 20K error suddenly becomes way bigger? MSE really punishes large mistakes. So when do you use which one? Well, if you have a crazy outlier, like your model was off by $1 million on one house, that one mistake would make your MSE score explode. MAE, on the other hand, would just treat it like any other error, making it more robust. And then there's the R-squared score. This one's my favorite, it's so easy to understand. An R-squared of, say, 0.85 just means that your model's features, like the number of bedrooms or the zip code, can explain about 85% of the differences in house prices. The closer to 1, the more of the story your model can tell.
Okay, now for a really cool scenario. Imagine you have a giant pile of data, but with 0 labels. No cats, no dogs, no house prices, nothing. And your job is to ask the computer to find any natural hidden groups or clusters all by itself. This is called unsupervised learning, and the star of this show is k-means.
Think of the k-means algorithm like trying to figure out the best place to open a few new coffee shops in a city. First, you just randomly guessed k locations on a map. These are your centroids. Then, for every person in the city, that's a data point, you figure out which coffee shop is closest to them. We use the simple Euclidean distance formula for that. So, if a person is at coordinate 3, 4, and a shop is at 1, 2, the distance is the square root of 3 minus 1 squared plus 4 minus 2 squared, which is the square root of 8, or about 2.83. Once every person is assigned to a shop, you do the update step. You find the center of gravity for all the customers of one shop, and you move the coffee shop to that new average location. Then you just repeat this whole process, assign, update, until the coffee shop stops moving.
Great, so we've found our clusters. But are they any good? Are they meaningful? That's where the silhouette score comes in. For every single data point, it measures two things. A, the average distance to its own cluster mates, its friends, and B, the average distance to the points in the next closest cluster, its neighbors. A score near +1 means that B is way bigger than A. The point is super close to its friends and really far from its neighbors. That's a great cluster. The Davies-Bouldin index is kind of the same idea, but here you want a low score, which means your clusters are very tight and very far apart from each other.
Okay, we've found lines, we've predicted numbers, we've found hidden groups. Now let's bring out the heavy artillery. Let's talk about tackling the really complex problems, with models that are literally inspired by our own brains, neural networks. For things like recognizing faces in a photo or understanding human language, simple lines just won't cut it.
So the basic building block of a neural network is just a single neuron. It's actually pretty simple. It takes in a bunch of inputs, x, and it multiplies each one by a weight, w, which basically says how important that input is. So let's say our inputs are 2, 5, and the weights are 0.5, -1. The weighted sum is just 2 times 0.5 plus 5 times -1, which is -4. Then you add a bias, let's say +1, so you get z equals -3. Now this z value gets passed to an activation function, which is like a little gatekeeper. A real U function, for example, would just output max 0, -3, which is 0. A sigmoid function would take that -3 and squash it into a number really close to 0. That final output is what the neuron decides to say.
Okay, another massive exam tip here. This is all about using the right tool for the right job. If you have a yes-no problem, like is this email spam or not, the very last neuron in your network has to use a sigmoid activation. It's the only one that squishes the output into a nice probability between 0 and 1. Then you use binary cross-entropy to measure how wrong that probability is. But if you're predicting a number, like a price, you just use a linear activation at the end, which basically does nothing. It just passes the number through, and you use the same old MSE loss we talked about earlier. Match the tool to the task. So neural networks are incredible at computer vision, at seeing. But here's the thing. They don't have eyes. They don't see pictures. They only see numbers. So before we can ever show an image to our AI, we have to perform a few really critical steps to translate that image from pixels into a language the machine can actually work with.
There are 3 main steps you've got to know. First, grayscale conversion. A color pixel has 3 numbers, red, green, and blue. This step simplifies it by using a formula to combine them into a single number for brightness. It just makes the problem easier. Second, normalization. Pixel values usually go from 0 to 255. We scale them down to a tiny range, like 0 to 1, by just dividing by 255. A pixel that was 127.5 becomes 0.5. This makes the network learn faster and more reliably. And finally, flattening. An AI doesn't see a grid, it wants a long list of numbers. So if you have a tiny 2x2 color image, that's a 2x2x3 grid, flattening just unrolls that into a single list of 12 numbers that we can feed right into the front door of our network.
So we've done it. We've built our model, we've trained it, it's making predictions. Now for the moment of truth. The final and arguably most important step is to evaluate it. We need hard numbers, objective scores, to know if our model is any good and to see if it's better than another model. It's time to grade its final report card.
And absolutely everything begins with this little box, the confusion matrix. It's the foundation for everything. Let's use a serious example, a medical test for a disease. A true positive is great. We correctly identified a sick person. A true negative is also great. We correctly identified a healthy person. A false positive is an error. We told a healthy person they're sick, which causes stress but isn't a disaster. But the false negative, that's the one that keeps you up at night. That's when you tell a sick person they're perfectly fine. Understanding this matrix is the key to all the metrics that follow.
Okay, let's put numbers to that matrix. Say out of 100 people, we get 8 true positives, 2 false negatives, 5 false positives, and 85 true negatives. Accuracy is just how often we were right. So 8 plus 85 divided by 100, that's 93%. Looks amazing, right? But hold on. Let's look deeper. Precision asks, of all the times we raised a red flag and said yes, which was 8 plus 5 equals 13 times, how often were we actually right? That's 8 divided by 13, which is only about 61.5%. Precision is about not crying wolf. Then there's recall. It asks, of all the people who were actually sick, which was 8 plus 2 equals 10 people, how many did we successfully find? That's 8 divided by 10, or 80%. Recall is about not letting a single wolf slip by. The F1 score is just a way to balance those two.
So now, let's just take a step back and look at the big picture, the whole machine learning pipeline from start to finish. See how it all connects? You always start by prepping your data. That's week 10. Then you choose and build your model, whether it's an SVM from week 6, a regression model from week 7, or a big neural network from week 9. After it's trained, you evaluate it, using all those metrics from week 11. And in the real world, you almost never stop there. You take what you learn from the evaluation and you loop right back to the beginning to refine and improve. Every single topic we've covered has its place right here in this process.
All right, to wrap this all up and really put your understanding to the test, I want you to think about this question. If you are designing a medical test for a very dangerous, life-threatening disease, what do you care about more? Do you prioritize high precision, which means you avoid scaring healthy people with false alarms? Or do you prioritize high recall, which means you find every single person who actually has the disease, even if it means you get a few more false positives along the way? The answer to that question tells you everything you need to know about why these formulas matter in the real world. Think about it. You've got this. Good luck on the exam.